Hello, everyone. My name is Dr. Garrett Struckoff, and today we're going to be talking about units and dimensional analysis. As you can see, our objectives here are to look at some examples of units, some different dimensions, and what the difference is between a unit and a dimension, converting units, and also some practice problems for you to work on your own. So what is a unit? A unit is an agreed upon quantity of something that can be measured, like, for example, a foot. A foot is a unit of length that we all kind of know what it means. We know that it's a certain length, and across the world, we agree that that's what a foot is. Now, in the rest of much of the rest of the world, they don't use feet to measure length, but they still know what a foot is. Or, if they do know what a foot is, they know how to convert that into the units that they do use. And in engineering and everyday life, units allow us to be more specific and are part of a complete quantity. So, for example, if your roommate's about to go to the store, they ask if you want anything, and you say, "Yeah, sure, grab me two." They're not going to know what you're talking about. It's an incomplete answer. You want 2 apples, 2 bananas, 2 atoms, 2 pounds, two of everything. And so it's an important distinction, because if you only give the number and you don't give a unit, you're not really giving a complete answer for many, many things. Unless your roommate's on the way to a store that only sells one thing, then, which I don't really know of any stores that only sell one thing, you're not going to be getting what you wanted from that. There are 7 base quantities from which other units can be derived algebraically. So if we think about the different kinds of units, some of them aren't listed here. Like, for example, density is not listed on this table as one of the 7, but density is derived from other things. It's derived from mass and volume. So as you can see, there's no area here, there's no volume, there's no force. So a quantity like mass is measured in units of kilograms in the SI system, and in units of slugs in the FPS system, which is what we use in the United States. So FPS just stands for foots, pounds, seconds. Length is measured in meters or feet. A temperature is measured in Kelvin or Rankine. Celsius, of course, and Fahrenheit are also ways of measuring temperature, but this is the fundamental way of measuring it. So Rankine and Kelvin both measure their absolute temperature. They measure back to absolute zero, versus something like Fahrenheit, which measures back to the point where an alcohol and water solution freezes. A mole is an amount of substance, so that's like the mass of it. Moles, or not the mass, but the amount of substance. Moles. Time is measured in seconds. Current is measured in amperes, and one that does differ between the two systems of units is luminous intensity, which is measured in candela in SI and foot candles in FPS. So what is a unit? For engineers, units are critical. Some instructors will grade an exam or homework response as completely incorrect if no units are given. And there's a good reason for that, because you have to know you have to remember to use units correctly. In school, you might not have thought about this, but school is a place where you want to make mistakes and learn from them. You don't want to not use units in your career, and because of that, cost millions of dollars on a project. Instead, we want to make those mistakes in school, get harshly reprimanded, such as losing all the points on a test problem. But that will hopefully drill into your head that you need to use units in the future. Exam and homework problems, like I said, they're carefully scaffolded, meaning that we write them in such a way, and we create them in such a way that they support you and bring you up and teach you. But in engineering practice, of course, that's not the way it usually works. You don't always know what the units are. In a problem that I give on an exam, generally speaking, you can guess what the units should be at the end just based on the answer. But in the real world, if you're building a bridge, someone doesn't know if you meant to put meters or feet if you're not specific, or even inches or feet if you're not specific. Length, area, volume, concentration, time, temperature, they all have widely recognized possible units, meaning that we don't know if you meant inches or feet or meters unless you tell us. That preference of unit choice can vary depending upon where you are. So if you're in the US, we usually measure things in acres. Most of the rest of the world uses hectares. Due to your discipline, chemists like to use molarity, capital M there, versus engineers, environmental engineers in particular, like to use milligrams per liter instead of molarity. And then also due to the age of the design. An older design might have things still measured in terms of chains versus feet. That was a kind of outdated, obsolete measurement, but it still does exist in older designs you're looking at. And like I said, it's not always possible to know what you meant to use. So you can't just assume that your reader, whoever's reading your result, will know that you meant to use feet or whatever unit you're looking at. SI units have very specific real constant quantities backing them up. So the second is the number of oscillations of a cesium-133 atom that can be measured. And then from that, that's what an atomic clock does. It measures those oscillations. A meter is defined as a distance that light travels in a vacuum during a very specific fraction of a second. An ampere is defined as a magnetic force between two conductors 1 meter apart in a vacuum. And a mole is the number of atoms in 0.012 kilograms of carbon-12. And I think you might notice that a lot of these relate to each other. So a mole is based on a kilogram, not a gram, because a kilogram is something that's defined by SI. And in fact, on the right-hand side, you can see a picture of the actual or an actual kilogram of material. I think it's silver because it doesn't corrode as much, but you can see it's also in 2 bell jars. So they're keeping oxygen away from that silver so that it doesn't corrode and turn into something else. So it's exactly a kilogram. Now, what's interesting about the SI system that differs from the FPS system is that these ways of defining the different units are universal, meaning they can be used anywhere in the universe. If you look, well, except for the kilogram one, that one's a little bit weird because it's kind of stuck here on Earth. But if you had that kilogram block and you brought it anywhere in the universe, you could use that to measure other things in terms of kilograms. The same is not true of a pound, because a pound is a unit of force. If you were to take a pound of something and put it on the moon, it doesn't weigh a pound anymore, and it weighs a sixth as much as a pound. So you can think about it that way. The everyday approach, like feet, inches, they're based on, like, generally speaking, body parts. Like a foot is how long a person's foot is. An inch is about as wide as a person's thumb. And that's just the way that they were derived back then. But now we use the SI system in particular uses very specific, universal. The way that cesium-133 oscillates is constant across the universe as far as we're aware. SI also uses prefixes. So we talk about meters or liters or hectares. You can also change that. So you might know, like, a centimeter, for example, is about a little bit less than half an inch. So a centimeter is a hundredth of a meter. So those will get our SI prefixes. Nano is a billionth of something, maybe a meter, maybe a liter. Micro is a millionth. Milli is a thousandth. Centi is a hundredth, like a centimeter. It's 100 centimeters in a meter. A deci is a tenth. We don't use deci much in the States, but deciliters are pretty common in other countries. Deca is 10. So a decameter would be 10 meters. Hecto is 100. Kilo is thousands. Mega is millions. Giga is billions. And tera is trillions. So these bigger ones we use a lot in data, right? We have megabytes, gigabytes, terabytes now. Petabytes is a thing now too. So about 1,000 terabytes is a petabyte. But yeah, anyway, moving on. I wanted to talk to you guys a little bit about what those are. Because I can tell you all day long that a nano is a billionth of something, but I wanted to give you some real life examples of what those might look like. So a nanometer, these are all going to be in terms of length. A nanometer is about the width of 10 atoms, if that gives you a hint of how small that is. So nanometer is actually very, very small. We use it to measure wavelengths of light, for example. A micrometer, so 1,000 nanometers, is the length of a bacteria. So a tiny little bacteria is about 1 micrometer wide. A millimeter, so 1,000 micrometers, a millimeter, is the thickness of a dime. If you think about how thick a dime is, that's a millimeter. A centimeter is about how long a staple is, like the common staple used in paper. A decimeter is about the width of a man's hand, so about 4 inches, about that wide. A decameter, DAM, so deca, the abbreviation for deca is DA. A decameter is the height of a 3-story building. A hectometer is the length of a soccer pitch. And just a little note here, sometimes we use hectares in engineering, and a hectare is an area that's equal to a square hectometer. So like hectometer, you break it down, it turns into hectare. So that just means 100 meters on the side. So hectare is 10,000, 100 squared, 10,000 square meters. A kilometer is about how far you can walk in 10 minutes. So a 10-minute walk is a kilometer. A megameter is the distance from our campus here at CSUF to Albuquerque. And interestingly, it's also about how far sound travels in 1 hour. So if you think about how fast the speed of sound is, a megameter, 1,000,000 meters, is about how far sound travels in an hour. The gigameter, so 1,000,000,000 meters, is the diameter of the sun. The sun is huge. So a billion meters across is the diameter of the sun. And that's how far it would be from us to the moon and back twice. So if you flew to the moon and back and then did it again, that would be the diameter of the sun, or roughly 1,000,000,000 meters. And then a terameter, a trillion meters, is the distance that light travels in 1 hour. So the distance from us to the sun is 8 minutes. That tells you it's 1 AU. So light travels from the sun to the earth in 8 minutes. it can travel 1 trillion meters in an hour. So that tells you how far, how big that is. So I hope that that's interesting to you guys, how just comparing, sometimes we might think nanometers, micrometers, those are about the same, but they're not at all. A nanometer is much, much smaller. We might think mega and giga are similar, but they're really not. One's the distance from us to Albuquerque, the other is the distance from us to the moon and back twice. I mentioned foot-pound-second units, FPS units, already a little bit, but they're also known as US customary units, and this just shows you a breakdown. In engineering, these really are not great, just because they don't have round numbers. So the SI system of units uses all powers of 10. The millimeter is, thousandth of a meter. It's easy to remember. Unfortunately, the FPS system does not use that, so we use something like 12 inches as a foot, 3 feet is a yard, 5,280 feet is a mile, 43,560 square feet is an acre, and 640 acres is a square mile. So lots of different numbers you have to remember if you want to convert among foot-pound seconds. I thought you guys might be interested in this if you cook at all. So 3 teaspoons is a tablespoon, 2 tablespoons is a fluid ounce, 8 fluid ounces is a cup, 2 cups is a pint, 2 pints is a quart, 4 quarts is a gallon, and then 7.481 gallons is a cubic foot. And that one you'll use a lot, actually. So remember 7.481 in your engineering practices. And then you can read the rest if you want. They're just a lot harder to convert among, but you can see we also have force and mass, we have power, we have temperature, lots of different ways to compare among units in the FPS system. Now, I mentioned before that a lot of units are derived from base quantities. So these are called derived units. Something like volume is length cubed, density, mass per volume, or weight per volume. Concentration can be mass per volume solvent, mass per mass, volume per volume, mole per volume solvent, that'd be molarity. In some cases, the unit will also be derived from base units. So density doesn't have a special unit, it's just pounds per cubic foot. Concentration, moles per liter, milligrams per liter. But that's not always the case. There are things like pascals, newtons, poise, and watts that are all actually named after people. So Pascal is a Newton per meter squared. So you have to kind of keep that in mind, that these named ones that are named after people are a little harder to convert among, because they're not just with density you get pounds per cubic meter or pounds per square cubic foot. It's easier to do unit conversions with that because you know what the units are in the derivation. Pressure is a derived unit. So pounds per square inch is PSI. Pascals is a 1 Newton per meter squared. A Pascal is a lot smaller than a PSI. So if you're converting among the two, just keep that in mind, that a Pascal is tiny. It's roughly 7,000 pascals is 1 PSI. So we normally report things in terms of kilopascal. So atmospheric pressure, for example, is 14.7 PSI. You can remember that. Or 101 kilopascals. And that's just easier to say kilopascal than to say 101,000 pascals every time. Something very useful for civil engineers is that material stiffness also has pressure units. So Young's modulus for steel, Young's modulus is the stiffness of a material. It's around 29 mega psi, or 200 gigapascals for Young's modulus for steel. For LDPE, low density polyethylene, like something like a milk jug, is closer to 0.033 mega psi, or 0.23 gigapascals. And one thing I wanted to put in here too is we often use KSI. You might see that in your units. KSI is just 1,000 psi, so kilo psi. And we do use SI prefixes somewhat commonly, like kilopounds. Actually, I should put that down there. Kilopounds, kip, is 1,000 pounds. So you often will see kips. So concrete is 3 kips per square inch, or 3 KSI. Now I wanted to talk to you guys a little bit about what the difference is between a PSI and a Pascal and why it matters, and a little bit about the material stiffness too. Because remember, we're talking about how pressure units are also used for Young's modulus, which is used all the time in concrete and steel design. So a Newton is about the weight of a lemon. And remember, Newtons are weight, not mass. So a lemon weighs about 1 Newton on Earth. A pound is about 4.5 Newtons. So about 4.5 lemons. If you look at a square meter, and you can compare here a square meter to a square inch is much, 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 much smaller than a pound. Sorry, than a square meter. But we talk about the atmospheric pressure as being 14.7 pounds per square inch, so 65 lemons on a single square inch. Compare that to a Pascal. A Pascal is 1 Newton per meter squared. So 1 lemon on that huge square meter of area versus 65 lemons on this little tiny square inch of a PSI. So this is again just to remind, just to kind of hopefully visually bring home the difference between PSI and Pascal. They might sound similar because they both start with a P, but really one is really 7,000 times bigger than the other one. Now, there's way too many units to mention in this short review, so I just wanted to give length. I like to go to, it's like digitaldutch.com has a unit converter online. So I just went to there and I looked at their list of things that they have for length, and it's huge. It's angstroms, astronomical units, AU, cables, chains, ells, fathoms, feet, furlongs, hands, inches, light years, meters, miles, parsecs, rods, yards, and that doesn't even include the whole suite of SI prefixes, because you could have macro chains or nano chains if you wanted to. So I just let you know there's way too many, but we can easily find conversion factors. So if we have one unit and we want to convert it to another one, we can look up the conversion factor, 25.4 millimeters per inch, for example, 3.785 liters per gallon, 7.481 gallons per cubic foot, and then I said before 43,560 square feet per acre. And if you have those conversions, then you can convert amongst different ones, different units. So it's the same quantity, it's the same amount of something, but you're using different units to describe it. So I think you know that if you have, a rope that's 30 meters long, it can be described in terms of feet. It'd be like about 100 feet, but it doesn't change the length of the rope by changing the units. So we're going to use the factor label method to do unit conversions here. Now, one thing we have to keep in mind, we can only do arithmetic of terms in an equation if we have similar units. So for example, if we have 1 apple plus 3 apples, I know those are actually just red circles, but 3 apples, we get 4 apples. That's easy enough to do. But if we try to compare apples and oranges, if we have different units, we can't compare. So 1 apple plus 3 oranges, it's like a fruit salad. We don't know what that is anymore. But what we can do is if we have a problem, so if we want to know the total area of 1.3 acres plus 2.1 hectares, we just need to convert the units of one of those to the other. So we need to convert either acres, 1.3 acres into hectares, or we need to convert 2.1 hectares into acres. In this case, it tells you in parentheses here, it tells us what units we want to have at the end. So we'll convert acres into hectares. So the factor label approach, the first thing you do, I also like to call it the railroad approach. The first thing you do is you set up a grid kind of like this. We've got a line and some slashes downwards to separate the different components of our units. And we start out by, so for example, if you had milligrams per liter, you would put milligrams on the top, liters on the bottom, and we separate the numerators and the denominators with this. So we start out with 1.3 acres because that's what we're trying to convert. We put 1 acre on the bottom is equal to 40, and this is, you could look up, by the way, a conversion directly from acres to hectares, but I wanted to do it using just the ones I know off the top of my head. So I know that 43,560 square feet is equal to an acre. And I also wanted to point out, the reason I really like using the factor label approach like this is when I was a student, the biggest problem I had with unit conversions was remembering whether I needed to multiply times the conversion factor or divide by the conversion factor. Like if I had 75 feet, it was hard for me to remember if I needed to divide by 12 to get into inches or multiply times 12 to get into inches. When you do the factor label approach, because everything you're separating out all the different components of the conversion. So I didn't just put 43,000 feet squared per acre. I put 43,560 feet squared is equal to 1 acre. So I'm essentially multiplying times 1. Two quantities that are the same over top of each other gives you 1, right? I know that 1 square foot is equal to 0.3048 meters squared. So I can square 0.3048. That'll give me, I just happen to know, like I said, off the top of my head, that 0.3048 is how many meters there are in a foot. Next question is, how many square meters are there in a hectare? And if you recall, I told you before, it is 10,000, because a hectare is 100. It's a square hectometer. It's 100 meters on the side. 100 squared is 10,000. So now we can go through and make sure that all of our units cancel out. And what we're going to see is that we're left with the unit that we're looking for. So we can cancel out acres, we can cancel out square feet, we can cancel out square meters right here. And sure enough, we're left with hectares as the only unit that's left. So what we'll do next is we go through and multiply everything across the top and divide everything across the bottom. 1.3 times 43,560 times 0.3048 squared divided by 10,000. Multiply across the top, divide across the bottom, and you're left with 1.3 acres equal to 0.528 hectare. And then we just add those together. So now we have two terms that have the same units, 0.526 hectare plus 2.1 hectare, and we're left with 2.6 hectares as our final answer. And just some good advice for you on exams in particular, make sure you box your final answer in, and that helps the grader go through and make sure that it makes the grading a little easier, and a happy grader is a better grader. So we're gonna do a couple examples. First, I want to convert 75 kilometers into feet. Okay, that's easy enough. So 75 kilometers. Set up my railroad thing I was telling you about. I know that a kilometer is equal, so I think about the units that I know. I know a kilometer is equal to 1,000 meters. Okay, so now if I were to multiply that out, I have my units in terms of meters instead of kilometers. I know, as I said before, that 0.3048 meters is equal to a foot. That's one that I learned in college and stuck with me. So 0.3048 meters is equal to a foot. Multiply 75 times 1,000, divide by 0.3048, and you're left with 246,063 feet. We double check, make sure we have the units that we were asked for. Sure do. We're looking for feet. And so that's our final answer. Next, I want to convert 3.14 cubic meters into gallons. So I start with what I know. I know I have 3.14 cubic meters, pi cubic meters. Use units that I already know, 0.3048 meters cubed this time, in a foot cubed. So I know the conversion between, and you could even say it's 0.3048 meters per foot, and then cube that. I know 7.481 gallons in a cubic foot. So I can cancel out cubic feet, cubic meters, and I'm left with just gallons. I forgot to cancel out meters in the previous one. I'm left with just gallons, and that's the unit that I'm looking for. So I do my multiplication, 3.14 times 7.481 divided by 0.3048 cubed, and I get that is 830 gallons. Not too bad, not too bad. Next, I want to convert 62.4 pounds per gallon into grams per cubic centimeter. To 2.4 pounds. This is one of the first examples where I have a unit that has two kind of base quantities in it. So 62.5 pounds per gallon. Gallon goes in the bottom because we're splitting out our numerators and our denominators. Multiply that times the number of liters in a gallon. Or let me go back. So we want to cancel out gallons. We're trying to get into grams per cubic centimeter. So I want to use terms that I know off the top of my head. I want to use unit conversions. And a lot of times on an exam, you'll be given unit conversions too. But I know that there are 3.75 liters in a gallon. So now I've canceled out gallons. Technically, now I have pounds per liter. I know that there are 1,000. I look at a liter, I have 1,000 cubic centimeters in a liter. A cubic centimeter is the same as a milliliter. So you can think about it that way. I could have said 1,000. Actually, I could have said 1,000 milliliters in a liter and 1 milliliter in a cubic centimeter. That works too. Now I can cancel out liters and milliliters. And so currently I have pounds per cubic centimeter. I just need to convert into grams now. So how many grams are in a pound? Just so happens that's 454. 454 grams per pound. And you could also do that. You know that 2.2 pounds is in a kilogram, and then 1,000 grams per kilogram if you wanted to do that too. We multiply across 62.4 times 554 divided by 3.75 divided by 1,000, and we get 7.49 grams per cubic centimeter. Next, I want to convert 45 megapascals into KSI. So that's 1,000 PSI. Start with 45 megapascal. Draw my railroad that I have here. I know that 10 to the 6th Pascal is equal to 1 megapascal. So that helps me start converting away from megapascal, so that cancels out. 10 to the 6th on the top. I know that a Pascal is roughly equal to a Newton per meter squared. Now this is a little bit weird because I have to separate out Newton and meter squared to the top and bottom, but that allows me to cancel out pascals, and now I have everything in terms of newtons and meters squared. I know that 0.3048, use this one a lot. Meters is equal to a foot, so I can square that. And now I have things in terms of newtons per foot squared. I know that a foot squared is equal to 12 inches squared. So now I have everything in terms of square inches, sorry, newtons per square inch. I know that a Newton, convert things to kilograms. I know that a kilogram is equal to 9.81 newtons. That gets back to Newton's law that F equals ma, mass times acceleration, and acceleration is 9.81 on Earth. Get rid of my kilograms. That's going to be 2.2 pounds. So now everything's in terms of pounds per square inch. I go through and cancel everything out. Inches, sorry, inches does not cancel. Kilograms cancels. Newtons cancels. So I have pounds per square inch. And I actually want it in terms of KSI. I know that 1 KSI is 1,000. Well, I can say 1,000 pounds is equal to 1 kip. 1 kilopound. So a kip is 1,000 pounds, and that cancels out pounds here. So the units are important to cancel as you go through because you need to make sure that what you end up with is what you started with, what you wanted to have. So we wanted to have KSI. I canceled all my units out. If I look around, all I have left are kips that hasn't been canceled and square inches that has not been canceled. And that's kilopounds per square inch is equal to 1 KSI. So I can do my math. 45 times 10 to the 6th times 0.3048 squared times 2.2 divided by 12 squared divided by 9.81 and then divided by 1,000, and I get 6.5 KSI is the answer that we wanted to find. So now we know if we were given a material that had a Young's modulus of 45 megapascals, which would be quite small, we can convert that into KSI if we're using FPS units instead. A couple practice problems for you. Speed of light is roughly 3 times 10 to the 8th meters per second. What would that be in feet per week? How far can light travel in a week in terms of feet? The Pacific Ocean has an average depth of 13,000 feet. It covers 60 million square miles. What is the volume of the Pacific Ocean in cubic meters? Good question. I hope this has been helpful for you for your understanding of units and particularly of unit conversions. I know that you'll be using this in future classes, and wish you the best.